All right, so we're going to derive Simpson's rule here. And the idea here is that as I mentioned before, there are so many functions whose antiderivatives we just cannot find. So it's useful to have some numerical strategies where you can just put it into a computer and generate areas under curves without having to find the integral. So this method is going to use parabolas to approximate the area under a curve. And we're going to put a parabola. In order to come up with an equation of a parabola, we need 3 points on it. And so we want to be able to approximate or to find the area underneath a parabola, because that's what we're going to use to fit into functions. Instead of trapezoids or rectangles, we're going to use parabolas. Now, one thing, the number of subintervals has to be even because we're going to need 3 points to determine a parabola. And so you can see here, to get those 3 points, we need 2 subintervals, right? So we always have to have an even number of subintervals. Now, we're going to find the area under this parabola, the one that I've drawn. And it doesn't matter that I've drawn it right so that the vertex hits the y-axis because its area would be the same no matter where I shifted it. So I'm going to label this x-coordinate negative h and this x-coordinate positive h. And so the points here are going to be h. I'm going to call this y sub 2, just the y value that corresponds to h. Here we're going to do negative h, and the y value, I'm going to call it y sub 0. And the point in the center is going to be 0, comma, y sub 1. So my goal is to find the area under this parabola in terms of these points. Right? Let me write that down. So our goal, find the area in terms of these points, because then I can use the area under this parabola to fit under any curve. So find area and express it using the 3 points. And another reminder here is that the standard form of the equation of a parabola is y equals, I'm going to call this ax squared plus bx plus c. So we're going to assume this parabola that we're working with has equation, in general, y equals ax squared plus bx plus c. And this h, this little piece here, h, that's going to be our delta x. Right? Delta x, when we break up an interval into pieces, if I'm looking at a function from a to b, is going to be b minus a divided by the number of pieces that we've broken it up into. We'll come back to this in a little bit. For now, we'll just call that h. Okay, so first thing, we're actually going to use integration to find the area under this curve. So to do this, to calculate the area, we're going to use integration. So I'm going to call this area under the parabola, a sub p, is going to be the integral from negative h to h. We know this function has equation ax squared plus bx plus c, and we're integrating with respect to x. We can actually find this integral, right? This is just a polynomial. So this is going to be ax cubed over 3, using the power rule, plus bx squared over 2, plus cx, and this is from negative h to h. Alright, now using the fundamental theorem, I'm going to put it over here, and we're going to put in positive h, so this we get ah cubed over 3 plus bh squared over 2 plus ch, and then minus what we get when we put in the negative h. So that'll be a negative ah cubed over 3 plus bh squared over 2 minus ch. simplify this a little bit. Right now, this is just a bunch of letters, but this is going to hopefully make sense in the end. Here we have AH cubed over 3 plus BH squared over 2 plus CH plus AH cubed over 3. So we'll have 2 of these minus BH squared over 2. That will cancel out. And then plus CH. And so we get an expression, 2 of these AH cubed over 3 terms and 2 of the CH's. That's the area. My goal is to express this area in terms of the 3 points. Because that way, if I have a big old function, right, here's the idea, some function f of x, and I split it up into an even number of pieces so that when I take 2 of these pieces, I use these points to fit a parabola. And we'll know how to find the area under that. Then I take another 2 pieces and use those 3 points to fit a parabola. Whoop. And I'll find the area under that. And then we'll do these 3 points and fit another parabola. So we need to be able to figure out what is the area underneath any parabola. That's what we're doing. We're doing that using integration so that we can actually do a numerical integration. I'm going to stop this video here. We'll continue in part 2.